Yeah. Yeah, my boss has the it's been a while. Take it easy, but I'm gonna keep going. Yeah, and it's pretty intense. I have
yeah, no, I mean, I'm paying.
Well, she said, come in, I'll give you.
see if I can get into there.
Have all my scholarships.
Do they do lumber?
Yeah,
They're a
it's
big thing.
like scholarships for me. I don't have any debt.
All right, let's get going on this thing. All right, I've had a couple questions on this one just to explain a little bit. Let's give this one more run because, we were really in the books, what you're given is something like that, and you work with it. But I just thought I'd throw something in there so you kind of understood how to get to that diagram. And the concrete, let's just look at that. Okay, the concrete is a flat slab, and it's, 0.625 meters thick, right? So that's what the concrete is. So what you do, you start off with the unit weight of concrete, which is 24 kilonewtons per cubic meter. All right, and that's how much concrete weighs per cubic meter. Now this particular slab is 0.625 meters thick, okay? So if you multiply the unit weight of concrete by that thickness, what you're getting then is what 1 meter by 1 meter weighs, okay? You all good with that? Okay. But what's happening here are these beams are put 2 meters on center, which means that the beam itself supports 2 meters of concrete, okay? So each beam supports that much concrete. So per unit length, each beam then, when you multiply that out, supports 30 kilonewtons per meter of length. See? That's how you're walking your way to that number. That's kind of trying to show you a picture there of what that means. So what we're saying here, we're looking at the beam that's holding this up. Each beam then per meter of length right there is accumulating 30 kilonewtons of concrete weight. So that's how you break that down from a concrete slab down to that lower portion of the diagram, the 30 meter height. So that's kind of the deal with that, okay? So you break it down usually first to an area unit weight by multiplying by the thickness, and then from there you can go to a linear unit weight if you multiply it by the width that it's holding up. Okay. And that turns that 3D problem into a nice, essentially, a one-dimensional problem. Really is for unit, weight per unit length. Now, if you look at the sand, see the sand is 0 right there, but over here it's not. It's bigger than 0. So.
And after you've got your linear density, you just divide by the 2 meters, right?
Well, if you use the 2 meters here, that is per beam right there. You could take the 4 meter width and then divide by 2. That would make sense too if you want to do it that way. Either way. Yeah. Okay. All right. So you all okay with that? All right. Okay, more Freebody diagrams then. So what we look at here, we draw a boundary around what we want our object to be. We look at the forces acting on the body, normally caused by physical contact plus weight. Okay. So what you look at then is the motion that the support prevents. So a cable will prevent motion that tries to stretch it out, okay? That's the type of motion that a cable prevents. Okay? But a cable does not prevent motion inward. So cables have to be in tension. They can't be in compression, okay? They only pull. Okay, there's some cables in actual photographs of things. Okay, a linkage is basically two, usually it's a narrow thin piece with two holes drilled in it. The force builds up between where the holes are drilled in the linkage. Okay, so they could be in tension or compression, but they can't have kind of offset loads alone, because if they do, they'll start to rotate, see? So the force is always directed from one hole to the other on a linkage. Okay, and they're called two force members for that reason. So there's a linkage on that chair that I've circled, okay? So notice that linkage would not prevent sideways motion. You know, the linkage itself won't do that. It's free to swing sideways. So the only motion it prevents is in towards the other hole on the link or away from it. Okay.
So does that mean that a link only has that it only needs to be able to handle compression? It doesn't care about tension or moments? Well, sorry, it doesn't care about shear or moment?
A link is tension or compression. Yeah, but it can't handle a shear or moment. It just doesn't, by itself, it doesn't do that. If you put links together and make like a truss, you can. But a single link, right, tension or compression, one or the other. Okay, nothing else. Okay, and then we got rollers, rockers, smooth surfaces. Again, see that the roller by its very nature is free to roll across the surface. So a roller is doing that, you know. It's free to do that, so there's no constraint parallel to the surface, but it can't move into the surface. And if you have basically a two-sided roller like I was showing you with that drapery rod, it'll prevent both motion away and from the surface, okay? But again, this thing's free to slide either direction here. Okay, so the force then is in the direction is normal to the surface. That's the idea. So you can have a 2D roller and a 3D roller, but the reaction force is perpendicular to the surface. Okay. What else do we got here? Okay, sliding collars are a little unusual, but they're like rollers basically. They'll allow the object to slide along this the rod in this case, either direction, but they can't move perpendicular to the rod. Okay, a pin joint will allow rotation, so the object's free to rotate on a pin joint, but it's not free to move up, down, or left, right. So again, the forces mimic the motions or create the motions that can't happen. So that rod that's attached to the pin joint can't move left, right, or up, down because it's bolted in. So as a result, there are the reactions for a pin joint, two of them, in normal to each other in either XY directions as I've circled, or over here on the other side in X prime, Y prime directions. You can orient them however you like. Okay. So here's some pin joints. This is the convention center down in Salem, or up in Salem maybe. There's some pin joints on those long thin tubes there that are holding the roof up. See the rivets in there? Here's the bridge crossing the Santiam River in Jefferson, the railroad bridge. Pin joint there, okay. Very commonly used on trusses, old trusses anyway. Okay.
Is that made out of iron?
Yeah, that's, truss bridges are kind of from the railroad era. It's kind of interesting, if you look at a few different places, like both Albany, Corvallis, and Salem, they have an old truss bridge, which is the first bridge. That's usually narrow and thin. The one out of Corvallis is a real problem, right? One lane, that's no good. And then the next step in technology was that concrete, that reinforced concrete. And that's the other bridge, that they use both at Albany and Corvallis. And that's usually those are that's 2 lane in Corvallis, that's easier. Okay. So you don't see these big iron truss bridges anymore. They're not efficient to construct. Okay. Okay, there's a piston down inside a cylinder on an engine there. See any pin joints on that? Yeah, I imagine you do if you look at it. Now, what you're looking for in a pin joint is basically some sort of rivet or a bolt or something like that that allows an object to rotate, but not to move up or down. So the pin joint there's one right there. Okay. Holds this connecting arm here to the piston itself. Have you seen any other pin joints? Kind of infers there is one more, doesn't it, when I say something like that? Unless I'm really trying to trick you, but I'm not. Where's the other pin joint on this? Right there, around the crankshaft, right? Because you can rotate around the crankshaft. Okay. So those are both pin joints, okay? There's a ball joint, which is a 3D pin joint right there. Not focused very well, but there it is right there. Okay. There's a ball joint. It's your hip. There's a ball joint. Trailer hitch, okay, that fits on top. Okay, universal joint is kind of like a ball joint. Probably commonly found in cars. That's a pretty high-tech duster there. It's got a industrial grade U-joint there. Okay, just have to remember to lubricate that every couple months just to make sure it's working well, but there you go. Yeah, I'm sure it does. I used to run a hay swather on a farm, and that was one of my jobs, was to make sure that things were lubricated properly. That was back in those days. So. What else do we got? We got a fixed connection on a collar, not a very common joint, but that would not allow rotation. So what you're getting now is a moment reaction, which you can have. More common case would be a cantilever. So a cantilever, it's like you've just taken a beam and embedded it in a wall, or maybe you've taken a floor joist and just kept extending it outside of a wall on a house. So it's just not going anywhere. So that's locked in. So you've got two force reactions and a moment reaction. Okay. So that's just a locked joint, basically. So when you prevent motion, that's when the motion you prevent are represented by reactions. So there's a fixed support. 4 bolts welded, pipes welded to a plate. This is a light post or something like that, embedded the bolts in concrete. That thing's just not going anywhere. So that's called a fixed support or a cantilever support. All right. All right, there you go. So that's just the basic pictures. On the next page, we got some examples. So what we got here is a funny looking little bracket thing with a few things on it. So now when you're doing free body diagrams, what you don't do is think too much, okay? Just look at the connections, draw in the reactions. Where people have trouble with these is when they start thinking too much about the effects of other things on the object. Okay, so if we're going to make that into a free body diagram, what are we going to do? And why don't I illustrate this? Okay, I see a pin joint. What happens at that pin joint? Where's the pin joint at? So, right up there at A. See, that's the pin joint. So I just focus on that. So I don't know which page we're on. We're on the one afterwards. When we get done. So, yeah, 570, 370, 370. Okay, thanks. 370. Okay, so there's a pin joint. I see a pin joint. What a pin joint does is it creates two reactions that are normal to each other. So I'd call that RAY, RAX. Okay. Now, sometimes people will say, wait a minute, that thing can't rotate. Isn't there a moment reaction at A? Because it can't rotate about A. But why can't it rotate about A? Does it have anything to do with the pin joint? Yeah, see, it's not the pin joint that keeps it from rotating. So all a pin joint does is restrain motion in the X and Y directions, so those are the reactions. Done. That's as much as I want to think about it. Okay? So don't think about it too much, okay? Okay, how about that roller at B? Everybody just think about that for a second, get the force on that. Yeah, I mean, you can kind of guess at the reactions. I mean, you got that weight at C, or excuse me, yeah, the weight there, and also you got the weight that goes through the center of gravity. So my guess is that roller force is going to do that, right? But if I guess wrong, if I had it going down left, it'd be okay. I'd still get the right answer when I ran the numbers, okay? You can kind of flip the direction and you're okay.
A roller like that couldn't produce a force in the other one.
Yeah, that's true. A roller couldn't really produce as shown, could not produce a down left force. But sometimes with the difficulty of drawing, you can kind of assume that even though it's drawn as, I don't know if there's a term for this, a one-way roller, sometimes they assume it acts like a two-way roller. Because it's just so hard to draw something like this. And so this is like a schematic symbol. But yeah, in this case, you're right. You know, I think that force will push up. Now, what's the relationship between the force and the ramp? 90 degrees, right? Okay, it's always that way. Now, you're given the ramp angle. What you want is the force angle. What's the angle of this force? Right here with the horizontal. And how do you get it? What's the geometry there that allows you to figure that out? Yeah, it's 90 minus 67. And I guess geometrically you could kind of derive that in different ways. I just think of it as a right triangle. That's a right angle. This is 67. So you got 180 and you take away the 90 and that leaves you with 90. So you don't even have to think about that step, but you're always going to have that 90. And then you take away the 67 and you get 23. So this angle right there is 23. So what you do is you take 90 minus the ramp angle, and that gets you the reaction angle. Okay, that's how that works. Okay, so 90 minus the ramp angle is the reaction angle. Okay. So just to emphasize this point, see, I could assume that this force goes the other direction. That would be fine, you know. If I assumed it down left, even though I really don't think it's going that way, but if I assumed that, I would still get the right answer. All that would happen is I get a negative answer instead of a positive one. However, what I cannot do, I can't assume that force is acting on some other line. I can't assume it's horizontal. If I do that, I'll get the wrong answer, okay? So you got to get the line right, the line of action of the force. You can flip it on the line, that's not a big deal, but you got to get the line of action right, okay? All right, so what I meant earlier, don't think too much, is when I see a pin joint, I look at the pin joint, I put an X and a Y force on there, and that's all I think about. I don't think about anything more. I see a roller, I put a force in there that's normal to the flat surface. I don't think about anything more, I just do that. And then, you know, the weight here and the weight of that bracket there, I would put in. We've got the 110-pound weight for the weight there that's hanging there, and the bracket itself looks like it's 40 pounds, so I put that on there. Okay, so there's my free body diagram, as they call it, or a force diagram, or whatever you want to call it. Okay, you good with that? All right, how about pulling the crate up the ramp there? There's friction acting on this too, so remember that. This one's pretty quick. There really isn't too much going on with this, but there's a few things that we want to pay attention to. Of course, there always are. Yeah, there's the weight. There's a few things. Mm-hmm. Yeah, I just sketch it up real quick, then we'll have a look. Okay, my inclination on this would be to set up an axis system parallel and normal to the ramp. Okay, because the friction is acting that way, the normal force is acting that way, and I've got that tension force already dimensioned to the ramp. So I just go ahead and work with it in that fashion, okay? So what I've got going on with that is I've got the weight which acts straight down. Now straight down is going to make a 17-degree angle with the vertical, same as the ramp angle with the horizontal. So the weight would make a 17-degree angle with the vertical. We got the normal force pushing up, the frictional force. Notice I converted the mass into a weight. Don't do statics with masses, do it with weights. And we got 600 newtons up and to the right. And see, I've got a little axis system set up like that. I think that would probably work better on this type of problem. All right with that? Okay. And that yellow outline, that's just drawing a boundary around the object, which can be a good step to go through with there. Okay, how about that beam being held up by a pulley? 1,700 pound beam. Draw a free body diagram of the beam and one of the pulley. Okay, remember that cables pull is what they do, and the weight acts at the center of gravity. Okay. So I did a little bit of trig there, got the angle, 4 by 6, arctan there. 33.7 degrees. So the pulley, those tensions are pulling down. On the beam, they're pulling up. So they act different ways depending on which object you're looking at. See, 1,700-pound weight down on the beam, that's going to equal the force up on that cable above the pulley. Okay, so which way those cable forces act depends on what it is you're analyzing. Okay, is there any questions on that? All right. Okay. All right. All right, let's say we got a lever there, pry bar, and we're going to apply that 300 Newton force. We got a fulcrum down there. That's the little pivot that the pry bar rotates around. It's not attached to the fulcrum. Draw a free body diagram of the lever. Assume friction's 0. On this one, pay some attention to getting the forces pointing the right direction. As I've mentioned, it's very important to do that. And that's actually why this one's in here is fulcrum. There we go. That's why I've got this one in here. Also remember to show what's happening to the bar. The deal is to draw a free body diagram of the lever, the bar, whatever you want to call it. I got space over there on the right for drawing this stuff up, but if you're on homework or a test or something, especially a test, I just make the object itself into a free body diagram. I wouldn't draw it all from scratch. It's just taking more time probably than you really want. So I would just take that object and turn it into a free body diagram. That's what I do. Okay. Okay. So the deal on this is those are smooth surfaces. The friction is 0. So the forces are normal or perpendicular, whatever you want to call it, to the flat surface. Okay. Okay, so here the flat surface is the bar, but here the flat surface is the board. So you got to identify what the flat surface is and then draw the force perpendicular to it. Also remember, we're showing not what the bar does to the board or what the bar does to the fulcrum. We're showing what the fulcrum does to the bar and what the board does to the bar. Okay, so just keep track of what you're drawing a free body diagram of and get the forces on there and the proper way to show that. Okay. Y'all okay with that? Got any questions on that? Okay. Everybody got that? Good to go? Okay. All right, so let's say here's just some things just around town and various places. There's I don't know, I wouldn't quite call it a monkey bar, but that's kind of the idea. I gave you a little zoom in on the support down there. So let's just look at some real life things and draw free body diagrams. So if you're gonna design this thing, and let's say we got a child a quarter of the way across the bar, what's your free body diagram gonna be? So have a look at that connection and model it in the best way you can. So what are those little bolted connections down there? How do you think you'd model them? Those look a lot like pin joints to me. Yeah, okay. Now, I kind of emphasize this sometimes, but our model is for a frictionless pin joint. Is that a frictionless pin joint? Probably isn't such a thing. Would you model it as such if you're designing this? Yeah, I think I would. Yeah, I mean, I'm not gonna. There might be a little bit of friction in there, but I'm not going to mess with it. I mean, I got other things to do to make money. Okay, frankly, okay, it's just not worth the time. Okay, I mean, if I'm designing a bridge, there is a gravitational effect of the planet Jupiter on the bridge, but what do I care? That ain't much. Okay, Okay, so there we go. Well, hopefully that shows up okay. So we got a child a quarter of the way across. Now that's a pin joint, so that gets 2 forces. Now as I have that drawn with the weight of the child going straight down, RAX and RBX are both going to be 0, I would assume, because there's no applied X force. However, I put them on there because that's a pin joint. It can't exert an X force, so I put it on there. I'm not analyzing anything yet. I'm just drawing a force diagram. In the analysis, I can show they're 0, but I put them on there. You know, I don't not show them. Okay. So, everybody okay with that? All right. Yeah.
Would you need to show a normal force or an opposing force to the weight of the child?
Those are the reactions.
Okay.
Yeah, so you know the reactions are what react to the applied forces. Yeah. Okay. Okay. Good. All right. From the playground, we'll go over to the oil fields here. So what do we got here? We've got this, it's called an oil derrick, I think. Okay, let's draw a free body diagram of that. There we go. That doesn't quite have the resolution I'd like, but you can kind of look at these fittings here and figure out what they are, you know. You ever see what those things will kind of rock is how they work. They rock back and forth and pump the oil. Okay, I'm thinking we got a pin joint there in at point C, plus the center of gravity's in there somewhere. Going to have a reaction at that pin joint, X and Y. And then we've got the cable at A pulling down. And then also, if you look at this thing, and you know, it's hard to see, but I would assume that's a link there, okay? Because this thing rotates, and that thing, if you watch it, it'll kind of rock back and forth. So that thing on our extreme right there, that's a linkage, I would assume. So that means it's basically what we call a two-force member. So the force goes right through the linkage. So that's why I've only got one reaction there. Okay. And then I've got center of gravity for the armature, and then for that head there, I've got a second center of gravity. So that's what I've come up with on that.
What if the pin for that cable is up near the top, and then it rocks, rolls off that top edge? Apply force this direction too?
If it were at an angle, yeah. Yeah, so if the cable were pinned up top and then it kind of came around like that, basically. Well, it would just depend. Now, the other thing is, it's a good idea to show the boundary. So how that cable's modeled depends on where you cut through it. If I cut through it down where I'm showing, it would just be straight down. But if I were to cut through it up here, it wouldn't. It'd be angled. So you have to pay attention, you know, of exactly where you're deciding to cut it. Okay. So even if you don't draw a boundary, it's worthwhile to imagine that, you know, if nothing else. Okay. All right. Good with that? We got any other questions? All right, we got one more here. Tell you what, this thing has 8,000 little signs and lights on it. How about just ignore the signs? Just have a look at that. That's a standard there for a stoplight, traffic control light. Okay, have a look at the connection there. I've kind of zoomed in on it. And also that beam there is a little bit tapered. You ever seen these things when the wind's really blowing? Those things rock and roll, man. When that's seriously, I mean, those things they're all over the place sometimes. I've seen them when the wind's really howling. So I'm sure they pay a heck of a lot of attention to that connection there, because that's where the stress really builds up. And you can see the size of those bolts. I mean, they're not kidding around with those bolts, are they? Okay. Okay. So what kind of connection, how would you model that thing with the bolts there? What is that? What do we call that? What's that? Cantilever, yeah. Fixed connection or a cantilever. That's just bolted in there. It's not supposed to go anywhere. Okay. And then you got a tapered beam extending out. It gets a little thinner as it gets further out. Okay, so a fixed connection, and my sketch is obviously a little bit busy, but why don't we just do it here? I think it was a good idea just to forget all the signs because it just clutters things up a lot. So we're going to call this RA, Y, RAX, and what? That thing's going to try and fall down that way, so this is probably going to be MRA, and then the weight. That's basically what I'm seeing, because I figured that, I don't know where the center of gravity is, but it'd be a little bit further to the right if that thing's tapered. Now I'm ignoring the weights of the lights and all that, but okay. All right. When I give you some of these Freebody diagram things to work on, now 251 through 255. And what you can do on this is just make the sketches right on that page. You don't have to redo everything, okay? And Not sure what page these things are even on. They're on page 12A and 12B. So you can just take those existing sketches and turn them into Freebody diagrams, okay? All right, so just take the sketches, turn them into Freebody diagrams. You don't have to draw them all from scratch. And just pull that page out of your packet and turn it in, okay? Or those pages, I should say. This is due Wednesday. Yeah. Is that the 1st of November, maybe?
Maybe, yeah.
Is it? Okay, thanks.